In this topology, we have one switch, which named switch 1, and 4 PCs. PCA and PCB belong to Vlan 10, which represent the sales department, and PCC and PCD belong to Vlan 20, which represents the IT department. Even though all 4 computers are plugged into the same physical switch, they cannot communicate with each other because VLANs create separate broadcast domains at layer 2. VLAN separates network traffic logically without needing to separate physical hardware, and this is
connect the PCA switch. PCC. PC4. Forward it. Now we will name it VLANs. In this part, I'm trying to connect the consider to the VLAN to have access on VLAN 10 and VLAN 20. Now, to check if these VLANs are now connected, we will use VLAN 2. And as you can see, there is consider net 1, and consider net 2, consider net 3, consider net 4 to their respective VLANs.
and now we will put their IP. PCB. And this time we will use the IP of 20 because they are in VLAN 20. And now to try it, we will use PD if they are connected. And as you can see, they are successful. What about the other VLAN? It is successful, but if we try to send PDU in PCA to PCC, failed. Let's try again. Failed because they are not in the same VLAN. Thank you. And now we will proceed in topic number 2, which is legacy inter-VLAN routing. To let the VLAN 10 and VLAN 20 communicate, the 2901 router uses two separate physical interfaces. The Gigabit Ethernet 00 handles the VLAN 10, and the Gigabit 01 handles VLAN 20. Traffic moves from PCA up through switch and gets routed at R1, which is the router 1, and passes back down to the switch and now to the PCB. This doesn't scale because it weighs a physical router port for every single network split. And now I will demonstrate to you how to do that. Now we will try to connect this Gigabit 01 into 5. To 6. Pass Ethernet to Pass Ethernet 1. And lastly, Pass Ethernet 2. And now I will now command in the switch in the router. The IP address of the VLAN 10. And we will take no shutdown so that it will not shut down. Now in the VLAN 20. Now no shutdown and exit. And now we will proceed in trying to command in the switch. Fast forward this so the orange is now gone. Now switch. SW1. And you're gonna switch one and now we will name the VLAN. Name C VLAN 20. Name is IT. And now we will proceed in trying to connect the switch link to router. So that says VLAN 10 06 for VLAN 20. VLAN 20. And now we will configure the switch links to PC. VLAN 10. And lastly, pass Ethernet 2 for VLAN 20. And to check that if it's in the VLAN, we will use show VLAN 3. And now we can see pass Ethernet 1, pass Ethernet 5 is in VLAN 10, name 6, and pass Ethernet 2 and fast Ethernet 6 is in now VLAN 20 in IT. Exit this, and now we will put the IP in their VLAN. This is what we use in IP address in router. And this is what we use in VLAN 20 in Gigabit Ethernet 01. Now to check it, we will use PDU, add symbol PDU in every PC. In first try it is failed, and now in second try it is successful. And now we will proceed in topic number 3, which is router on stick or ROS. Router on stick optimized legacy routing. Instead of running 15 different cables, we only used a single physical gigabit trunk link between router port gigabit 00 and switch port gigabit 01. On our router 2901, we divided the physical port into 3 logical sub-interfaces, the 10.10, 0.20, and 0.30. Each sub-interfaces tags and processes its own VLAN data, say VLAN sales, VLAN IT, and VLAN HR, using the encapsulation.1q command later that I will use. They serve as the default gateways for our workstations, completely solving our port scalability problem. Now I will demonstrate a quick ping test to prove that our inter-VLAN connection is successful. But before that, I will use this. And from this, we will use pass Ethernet 01 to PC1. This 5 PC holds the VLAN 10, which is sales. Now we will proceed to this PC6 and to PC10, which is the VLAN 20. And to this PC11 to PC15 is the VLAN 30. And now, after this, we will use the command encapsulation in our router. We will just post in R1 00 And in this part, we will put the sub-interface for VLAN 10. Point 10. For indicate point 10 because it is the indicator for VLAN 10. Now use encapsulation. We will put the IP address for the default gateway. And then submit plus. Now proceed to VLAN 20. And put the IP address of VLAN 20. And then submit plus. Next it again. And we will try to put the VLAN 30. And IP address for VLAN 30. Submit plus. And after that, to show that it is running, we will use show run. And as you can see, there is encapsulation in VLAN 10 and VLAN 20, and last VLAN 30 with their IP address for default gateway. Now we will proceed in naming the VLANs in switch. Okay. Now naming the VLANs VLAN 10, and the name is VLAN sales. VLAN 20, which is name IT. VLAN 30, name HR. And now exit. Now we will configure the trunk interface on gigabit 01. Now it is now in trunk, and exit again. And now we will assign the access ports for all our pieces, the 15 pieces. Pass Ethernet 0, 1, 2, 5. Pass Ethernet 1 to 5 is for VLAN 10. Oh. The range, I forgot. Access, we will giving access to pass Ethernet 1 to 5 in VLAN 10. And now exit. Proceed to pass Ethernet 6. 0, 6 to 10. 6 to 10 that handles the VLAN 20. VLAN 20. Exit again. This FA 011 to 15 is the one that handles that VLAN 20. And okay. Let's see if it's running. Now as you can see, VLAN 1 to FA0 1 to 5 is now in VLAN 10 sales, and pass Ethernet 6 to 10 is now in VLAN 20 name IT, and pass Ethernet 11 to 15 is in VLAN 30, which is HR, and now active. And now we will update the IP configuration. We will just copy this to have it easy. PC2, 11. The default gateway is correct. The subnet mask is correct too. This 12 correct too. Now 13. press enter to have it now in pieces. Now we will proceed in VLAN 20. Copy this. Correct subnet. It is now 12. 13. And lastly 14 with correct subnet class. And now we proceed in this PC11 to PC15 is the VLAN 30. Copy this. Then now we will double check if the IP configuration is correct. 10 correct, 11 correct, 12 correct, 13 is 13 correct, and lastly 14. And to check if all these pieces are now connected, we will use add simple PDU, send it to the same VLAN. Yes, it is successful. And for other VLAN, let's try it. VLAN 10 to VLAN 20. First it failed, but in second, now it is successful. Now we will use it PC1 to PC11, which is VLAN 10 to VLAN 30. Failed, but it is now successful, as you can see. And that's all for ROAS. And now we will proceed in topic number 4, which is Spanning Tree Protocol, or STP. STP prevents dangerous layer 2 switching loops. In this triangular topology, broadcast springs would loop endlessly and crash our network if all paths stayed active. By modifying the bridge priority to port 096, we force switch 1 to become the root bridge. This STP then calculates the best loop pre-paths and safely puts the redundant link on switch 3. This pass Ethernet 02 into blocking mode, which is why we see the orange indicator light. This completely eliminates network loops while maintaining a backup path. Now, I will run the verification command on our root bridge to show the STP status. This switch 1, we will configure this. Enable active spanning tree VLAN 1 priority port 096 and end and proceed to switch 2 to configure our passenger end. And to show that it is running, we will use this show spanning, and as you can see, we have it is enabled now, the route ID, bridge ID, and the passenger net 01, passenger net 02. FPCR10, spanning 3, port pass. Yes. Spanning 3, PPB guard enable. And now proceed to switch 3. Then end. To show that the spanning tree is connected, we will ping the PC1 and PC2 in command prompt. Ping what is the IP 192.168.1.20. And now as you can see, it is successful, but now we will ping the other PC. Command prompt. And it is successful. And as you can see, the packet successfully reached their destination, even though the direct link between switch 2 and switch 3 is physically blocked by STP prevent loop. The data is automatically rerouted up through our root bridge switch 1, confirming a fully functional loop-free network. That's all. For topic 5, we are configuring Etherchannel, also known as link aggregation. Inside our 3-switch network, normally, if we connect multiple parallel cables between switches, spanning tree protocol will block the redundant links to prevent a switching loop, leaving perfectly good cables completely idle. By implementing the Open Standard Link Aggregation Control Protocol or LACP, we successfully bundled our physical interfaces into 3 logical pathways: port channel 1, 2, and 3. This allows the switches to treat each pair of cables as a high-speed link, effectively doubling our bandwidth capacity between switches while providing seamless hardware redundancy. Because our port channels still form a physical triangle, spanning tree protocol automatically interfaces with our bundles. This putting port channel 3 into a blocking state to preserve a loop-free environment. And now we will configure now in switch 1. Active is now up, and then exit to 4, which is for channel group number 2, and then exit again. We will now in the interface port channel 1 that we will hold up. Is now up, and then exit again. Punta tayo sa port channel 2, and trunk again, and then right memory to save it. To show that it is running, we will use this show run, this trunk, port channel 2, trunk, passenger net 1, 2, 3, 4. It's connected now. And we will be going to configure now the switch 2. FT 2 channel group 1 mode active. I forgot the range. Okay, now we will be going to proceed and go to the interface for channel 1. Go back again, correct, and then interface for channel 3 and switch port mode back again, and then end and write memory to save. And to show that it's running, show run. The port channel 1 mode rank, port channel 3 mode rank, successful, and then 1 and 2, 3 and 4. And this spanning tree, because we use the spanning tree before. And now we will proceed in switch 3. One, two, two. This is now the channel group 3 because this one 3. See? Then 3 to 4. This will be now the channel group number 2. Channel group number 2. It's now up and then exit again. Now we will be configuring the port channel. Successful. And then port channel 3. Successful, and then and write memory. To save it. To show that it's running again, we will show run. And then port channel 2 and 3. Successful. 1, 2, 3, 4. Good. And to verify our link aggregation, I will run a verification command on switch 1. This is the reader show reader channel. Now group 1. And as displayed in the summary, our channels are plug S, this, plug S for layer 2, and U for in use, proving that our Etherchannel bundlers are fully active and operational. Finally, I will test end-to-end connectivity by opening the command prompt on PC1, this, and pinging the PC2 at 192.168.1.20. And the ping is successful. Our data frames are safely traversing the active Ether channels, validating a high-performance, fault-tolerant network topology. Thank you. For topic 6, we are demonstrating Hsrp or Hot Standby Router Protocol to achieve layer 3 default gateway redundancy. As shown in our topology, we have two physical routers connected down to the single switch. Instead of pointing our PC to a single physical router interfaces, which creates a single point of failure, we will configure router 1 and router 2 to share a single virtual IP address of 192.168.1.1. Router 1 will be configured as our active gateway, while router 2 will act as our standby backup. 0, 1, 2, 3. And next, I will open the switch 1 CLI to configure it. Enable.
terminal SW1 now 01 mode access, then no shutdown, F302 mode access, no shutdown, F303 mode access, no shutdown. And to check that if it's running, we show run. Okay, no, pass Ethernet 1, pass Ethernet 2, pass Ethernet 2. And I forgot. 80 is running. Okay, Vlan 1 priority 1096. And end. Show run again. Okay, it's running. Now, and next, I will open the router 1 CLI. I'm configuring its physical interface with the IP 192.168.12, turning the port on and assigning it to Hsrp group 1 with our virtual IP of 192.168.1.1. By giving it a priority of 110, we ensure this router becomes the active path. Now I will configure it. Terminal. Okay. Then HOR1. And it's gigabit 0 with its IP address of 192.168.1.2 and its subnet mask. Then we will make it no shutdown. And we will proceed by commanding the standby IP. IP priority, no priority, no IP, and standby again. Then end, and write my work. And to check that if it's running, so run. It's running again. Next, I will open the router 2 CLI to configure the backup path. I am assigning its physical interface the IP of 192.168.1 and 0.3, enabling the interface and joining the exact same Hsrp group 1 with the shared virtual gateway address. Enable. Okay. R2 interface gigabit 00 with its IP address of 192.168.1.3 and its subnet mask 0. We will make it more again. The priority 90 is because it is the backup one router. It is the standby. Standby for memory and then check again. It is running. And to verify that our protocol has negotiated correctly, I will execute the show standby brief command on router 1. Show standby brief. And as displayed in the table output, router 1 local state is successfully running as active. This. It recognizes its standby peer at 192.168.1.3 and our shared virtual IP is active too. And to prove high availability live, I will open the command prompt on PC1 and start a continuous ping until 50 or 100, targeting our active router physical interfaces. But first, I will have this IP. And now I will ping it. Ping 192.168.1.1. And for how many times I will ping it, and I will try to ping it 100 times. And start. And now, I will simulate a critical hardware failure by shutting down router 1 active interface while this is pinging. And interface G00 shutdown. And now it is down now. And let's see what happens in the pinging. Request timeout. But and as you can see, after losing only 3 packets during the quick failover negotiation, router 2 immediately notices the missing heartbeat, takes over the virtual IP address, and seamlessly resumes forwarding our traffic. This validates a highly redundant network design with zero manual intervention. Thank you. For topic 7, we are demonstrating static routing, which involves manually teaching separate routers how to drop packets into distant external subnets. As shown in our topology, we have router 1 managing local network LAN A and router 2 managing LAN B. They are connected directly over a point-to-point WAN network using 10.0.0.0/30 subnet. Because these networks are completely isolated from each other, we will configure explicit static routers on both devices so they know exactly how to drop packets destination bound for the opposing LAN. Before configuring our routers, I will set up the end devices, opening the IP configuration for PCA. I will assign it a static IP address of 192.168.10.10 with a standard class C subnet mask. I'm setting its default gateway to 192.168.10.1, which points directly to router 1 local interface. And now I will do it. Configuration 192.168.10.10, and its subnet mask is here, and point 1, point 10.1, point 10.1. And now it's okay. Now I will open the IP configuration for PCB on the right. I will assign it the static IP address 192.168.20.10 and set its default gateway to 192.168.20.1. 168.20.10 and point 1. This establishes the gateway address that PCB will use to exit its local subnet. With the endpoints ready, I will open router 1's CLI. I'm configuring its WAN interface facing router 2 with the IP 10.0.0.1 and its local LAN gateway interface with 192.168.10.1. Finally, I am adding the manual static route telling router 1 that to find the 192.168.20.0 network. It must forward packets to the next hop IP of 10.0.0.2. Enable. Now, 6 gigabit 00 IP address 10.0.0.1 255 this is slash 2 and not one. That's it again. And interface G01 address 192.168.10.1 and 255 0. No shutdown again. Exit again with its IP route 192.168.20.0 255.255.255.0 and the IP address of gigabit Ethernet 00 and F write memory. To show that it is running, we will use the command show run. This is running now. And IP route 2. Next, I will open router 2 CLI. I'm configuring its WAN link with the IP 10.0.0.2 and enabling its local LAN interface at 192.168.20.1. And I will also apply the return static route, instructing router 2 to drop packets heading towards LAN A of at router 1's 1 IP of 10.0.0.1. Oh, then 0, 0, 10.0.0, 2, and 2.1, 2.2. No shutdown. That's it again. 1 with its IP address. No shutdown. Check it again and use the IP route. This IP route purpose is to connect the two routers. Check if it's running. It will show run. Now we can see the gigabit Ethernet. It is now in the interface gigabit 01 and 000, and the IP route is now configured. And we can now to check our router's navigation ledger. I will execute the command show IP route static right here on router 1. Show IP route. Show IP route. Start. And as displayed in the table, the entry prefix with the capital S confirms that manual static path statement is active and correctly loaded into the routing table. And finally, to test our end-to-end connectivity, I will open the command prompt on PCA and send a ping across the one PCB at 192.168.20.10. Command prompt of PCA, ping D 192.168.20.10. 192, again, ping 192.168.20.10. And as you can see, the packets are successfully traveling back and forth across the routers between these two distant networks. This completely validates our static route and IP configuration. Thank you.